my name is Blaize, and I conducted this study at Lakehead University, and I was supervised by Dr. Noel Phillips. So this project is basically looking at uh, deformation and seeing if it is possible and how it can remobilize gold in Archean greenstone-hosted gold deposits. So for our main research question was, does deformation concentrate gold in Archean greenstone-hosted gold deposits? So a bit of a motivation for this project was actually another master's thesis that was conducted in 2022 at the Goliath Gold Deposit site. And this is just a figure here from that paper. A key observation that they made was that there's actually two generations of pyrite. So there's the first generation pyrite 1, which is highlighted here by this dashed red line. And pyrite 1 is said to be generally inclusion rich, including gold and silver. And then there's a subsequent second generation. In this case, it is the overgrowth on the pyrite 1. And these are generally inclusion poor and lacking gold and silver. So we hypothesized that deformation at the Goliath Gold Deposit resulted in significant modification of the main zone, which is where the bulk of the ore is found, and it's responsible for the visible gold that we see in the quartz veins at that deposit. So how can we test for a hypothesis? First, we want to establish some metamorphic conditions. So for this, we're going to be using petrograph, like light microscopy, as well as geochemistry to produce some PT phase modeling, as well as for EBSD. Then we want to determine some deformation mechanisms. So again, we'll be using light microscopy to look at quartz textures, as well as EBSD to image lattice distortion. And then finally, we want to document some textural relationships between quartz gold and the pyrite. So I'm quickly going to talk about some of our quartz analysis methods, just because the bulk of this project is uh, on the centimeter to um, micron scale. So these are very important observations for us. Starting quickly with dynamic recrystallization of quartz. This can be broken out generally into three different regimes, starting with the lowest temperature regime. This is the dominant mechanism at temperatures below 400 degrees C, and it's bulging or crystallization. And it generally produces a texture that looks something like this, where you have these little bulges, I guess, forming on the boundary of the quartz veins, on the quartz crystals, sorry. And these would be protruding into neighboring quartz crystals. Then moving on to subgrain rotation, this becomes a dominant recrystallization mechanism at temperatures between roughly 400 and 500 degrees. And it produces this characteristic texture here, where we have an abundance of subgrains, as well as these recrystallized grains, and they generally share the same grain size. So finally, looking at grain boundary migration, this becomes a dominant mechanism above temperatures of 550, and it produces a texture something like we see here. And so this is described as larger recrystallized grains with intergrown crystals. These grains generally have a serrated to lobate grain boundaries, and you can also see chessboard extinction in these crystals as well. So talking a bit about EBSD. So EBSD is an SEM-based technique, and it can be used to image misorientation in the crystal lattice. So looking at the figure on the top right here, important thing to note is that in panel A, different colors basically just represent different orientations of the quartz crystal. And so looking at this crystal here, this orange quartz crystal here, in the crystal, we can see that there's a change in shade of the orange to a reddish color. And basically this is telling us that there's some amount of misorientation or lattice distortion within that quartz crystal. And you can produce a couple different plots to display this information in different ways. So these will be some pretty important techniques for us. A bit of background about the Goliath Gold Deposit. So it's located within the Eagle-Wabagood Manitou Lakes Greenstone Belt, roughly 20 kilometers east of Dryden, Ontario. This deposit has had a couple different interpretations in the past. It's been modeled as shear-hosted mesothermal gold, VMS, magmatic hydrothermal lode gold, as and most recently synvolcanic gold deposit. So the morphology for this deposit is a result of two main deformation events. D1, which is north-south shortening, which produced some tight isoclinal folds, followed by D2, which produced the a D2, which is a north-northeast, south-southwest dextral transpression, and this produced these open folds you see here on the map. So the main zone is where the bulk of the ore is at the Goliath Gold Deposit, and this is where most of my samples will be coming from as well. So a bit about the lithology sampled for this project. So in panel A here at the top, we have the biotite muscovite schist. And below it here, we have the muscovite sericite schist. So these two rock types dominate the main zone. And so this is where most of the gold is found. The main differentiation between the two is just the amount of biotite versus muscovite. And this is important for us because we'll be getting all of our quartz and gold samples here for our observations. Looking at panel B, we have our mafic volcanics. We classified these as amphibolites based on thin section work. And so these will be important for metamorphic observations as well as our PT modeling. And then in C here, we have some of our metasedimentary rocks. And again, these will be important for metamorphic observations as well as our PT modeling. So now looking at a couple of thin sections here. On the left here, we have a thin section scan of one of the amphibolite samples. And as you can see, it's dominated by amphiboles with some garnets and plagioclase. So we characterize this as an amphibolite. And so that tells us that we're probably somewhere in the amphibolite facies, or we are somewhere in the amphibolite facies. On the right here, we have our more palitic metasediments. And this one contains a couple interesting metamorphic minerals. There's an abundance of storlite here. Just a bunch of these little guys here, just peppered throughout the sample. There's also a couple very small garnets. There's a blown up image of that here. And we also have quite a large cordierite crystal here as well. And so because we have cordierite in this sample, this is telling us that or because we have cordierite, it was generally a high temperature metamorphic mineral. This is telling us that we're probably somewhere in the amphibolite facies as well. And so it's good that these two kind of agree and tell us that we're probably somewhere in the amphibolite facies. Then we did some geothermometry work. On the left here, we have titanium and biotite. And on the right here, we have some titanium and quartz data. So the main takeaway from these two is that they gave us two different temperature ranges. The titanium and biotite gives us a higher temperature of roughly 728 degrees C. And we think this represents peak metamorphic conditions at the Goliath Gold Deposit. Whereas the titanium and quartz gives us a lower temperature, average is about 592. And we think this represents the temperatures of deformation at the Goliath Gold Deposit. The reason for that is that titanium in the quartz is known to resetting during dynamic recrystallization. And so the titanium values in the quartz are representative of the temperatures during the last deformation event. And so these are interpreted to represent temperatures of deformation. So looking again at some of our PT modeling, these pseudosections we have made. On the left here, this is created from the metapolitic sample I showed you a couple slides ago that contained the cordierite, the storlite, and the garnet. And so, important thing to take away from this is that the storlite and the cordierite don't actually overlap. Um, the storlite is giving us a temperature range of 550 to 600, where the storlite should be stable. And this is reflective of the titanium and quartz data. Um, there's some nice overlap there, where we believe the bulk of the deformation was occurring at the Goliath Gold Deposit. The cordierite data, or the cordierite rather, is stable at temperatures above 600 in this specified PT space. And this overlaps nicely with the titanium and biotite data, where we believe that this overlaps nicely with the peak metamorphic conditions we believe occurred at the Goliath Gold Deposit. So moving on to this one here, this is a pseudosection created for one of our amphibolite samples. Important thing to note here is that we have some garnet isopleths plotted here. Here's the core composition for that garnet, this yellow diamond here. And this red diamond here is the rim. So you can see that the garnet here actually preserves some zoning. So we can use this to learn something about metamorphic conditions as well. So based on the rim compositions, we can say that this garnet experienced peak metamorphic temperatures somewhere around 730 degrees C, which overlaps nicely with the stability field of our cordierite. That also overlaps nicely with the temperatures that we're getting from the titanium and biotite data. And so from all of these two pseudosections that we created, as well as the titanium geothermometry, we can learn something about the PT path for the Goliath Gold Deposit. So while this garnet was growing, there was an increase in pressure and temperature. It reached a peak about 730. And then from our titanium and quartz data, we know that it came back down in temperature somewhere around 600, where the bulk of the deformation was the Goliath Gold Deposit. And so from this, we can see that we're somewhere in the amphibolite facies. So now looking at some of our quartz microstructures. On the left here, we have a thin section scan of one of our quartz veins. And just looking at the texture in the quartz, we can see that the quartz is foliated. It appears to have like an intergrown texture. It has the lobate to serrated grain boundaries. And so to me, this looks like grain boundary migration. We then did an EBSD scan of the top left-hand corner here of that quartz vein, and we produced this misorientation plot here. So important thing to note is that the bright yellow colors represent 10 degrees of misorientation, while the dark blue colors represent 1 degree of misorientation. So looking at all the quartz here, we can see that there's a good amount of misorientation or lattice distortion. Looking specifically at any one of these crystals, this is a good example here, but a majority of the misorientation is concentrated along the margins of the quartz grains. And we can see that with most of the crystals here as well. And so this is kind of what we would expect if we think that our quartz is deforming through grain boundary migration. So as the quartz is deforming, the dislocations are being swept to the margins of the crystal. And this is producing a high degree of misorientation before they're then expelled at the grain boundaries. So another thing we did is we produced some ODF plots. These are basically just like stereographic projections. Looking at this one specifically, it's a stereographic projection of the 001 or the C-axis. And so you can see there's a strong point maxima here, which is basically just telling us that all of the quartz have the same orientation within the area, the EBSD scan area. And so all of this is telling us that our quartz veins are recrystallized. They're recrystallizing through grain boundary migration. Looking at some of our sulfides now. On the right here, we have two, again, misorientation scans. Um, this is just a scan of the pyrite. These pyrites are enveloped by quartz. Important thing to know is that they both do show a decent amount of misorientation. So this is suggesting that there's some lattice distortion as well. And so these are probably deforming through dynamic recrystallization. Now we were only actually able to index pyrite. The other sulfides didn't really index well, but I'm just going to zoom in here. Even without the EBSD scans, just looking at a reflected light image here, this light gray is galena, and we can see these little pits and scratches appear to be folded as well. You can see down here, a little bit over here, and up here as well. So this is telling us that our other phases like galena, our other phases like galena are also experiencing some amount of crystalloplastic deformation as well. Uh, Important thing to note too is that sulfides, particularly pyrite in this case, experiences the most lattice distortion when it's enveloped by quartz versus when it's caught up in the matrix or even um, enveloped by other sulfides. And that, based on the relationship, the textural relationships between the sulfides and the quartz, we can say that the sulfides and the quartz are deforming at the same time. So looking at a bit of our gold microstructures, here are two scans of some recrystallized quartz veins. This top one here, we have a bit of electrum with some other sulfides as well. And down here we have a little piece of gold. In this case here, the gold is completely enveloped by quartz. In the case of electrum, it's associated with some other sulfide phases, but relatively small amount. Just for reference, this is the same thin section that had the deformed galena that I showed previously. And this bleb here is that galena. There's some more sulfides here, and sulfides here as well. So it's a relatively small amount. And so usually when we find free gold or electrum, it's not really associated with other sulfide phases. It's occurring along the grain boundaries of the recrystallized quartz. And anytime we analyze these quartz veins that have gold or electrum, anytime there are sulfides present, they also show signs of lattice distortion or dynamic recrystallization. So from all of this, we kind of were able to put together a model of how we think gold is being concentrated at the Goliath Gold Deposit. So perhaps initially there's some uh, sulfide phase that contains the gold, sulfide phases that contain the gold. Maybe it looks something like this. These sulfides are then remobilized by some fluid to produce these veins we see here. Maybe it looks something like this, where you have your quartz vein that's entrapping these sulfides. Maybe there's some more sulfides occurring along the margins of the gold vein, but the gold is still typically found within the sulfides. Through deformation, the quartz veins, in this case, experiencing grain boundary migration. Any gold is dispelled or expelled from the quartz, either as inclusions, similarly for the pyrite here. And then we would expect to see that these little gold grains would concentrate along the grain boundary. And over time, these would produce sizable chunks of visible gold. Over further deformation over a prolonged period of time, we'd expect to produce a very deformed rock with a series of these like veins or veinlets where gold is found um, occurring along the grain boundaries of these quartz veins. But some of this gold will be expelled to the margin of the gold veins, and they'll be entrapped in the matrix, increasing the value of gold in the host rock as well. And that might produce something that looks like this, where you have a highly schistose rock with these little um, veins or veinlets, quartz that have some sulfides and gold. And this is typically what we do see at the Goliath in the main zone at the Goliath Gold Deposit. And so just to quickly summarize, the Goliath Gold Deposit reached peak metamorphic temperatures at 728 degrees, but we believe it deformed at a lower temperature of 592 degrees. The quartz veins experienced dynamic recrystallization through grain boundary migration in this case. Pyrite also shows good evidence of dynamic recrystallization, even though we weren't able to index other phases with EPSD, other phases like galena also show good evidence for dynamic recrystallization. Visible gold is always found along the grain boundaries of the recrystallized quartz within these quartz veins. And so we're proposing that dynamic recrystallization likely concentrated gold at the Goliath Gold Deposit. And we think that similar processes can also concentrate gold in other Archean greenstone hosted gold deposits. Thank you.